Hello, all. I hope everyone is having a good day so far. We got some notes to take. Are you excited? I'm very excited. We're actually starting, or have been starting, a new topic. So I hope you enjoyed that movie because this new topic is all about ionic bonds. And the video briefly mentioned this, but we're going to be talking about why sodium and chlorine would react. And to start with, I'm going to go ahead and I'm going to draw out a Bohr model of a sodium atom and a Bohr model of a chlorine atom. 11 protons. Let's go down now. 12 neutrons. 1, 2. Actually, I learned a cool trick. It was supposed to be a circle. 1, 2. Hold on. I'll get it. There we go. There we go. 1 shell. 2 shells. 3 shells. And sodium has 1 valence electron. So that's Na. And this is going to be Cl. Oh. Let's do 17 protons. Let's do 17 neutrons. We got 1 shell, 2 shell, and 3 shell. We have 7 valence electrons. 7 electrons. Okay. And where am I? No, there I am. The reason that sodium and chlorine would even bond in the first place has to do with something called the octet rule that we probably went over in class, but I'm going to go over it again. And the octet rule states that elements tend to want, or tend to have, elements don't really have feelings, they don't want. Elements, really off my game today. There we go. Elements tend to change to have 8 valence electrons. And that's simply because, as it turns out, 8 valence electrons tends to be more stable. Is it always the case? No. But that's what it tends to be. Now, even though we're calling it octet rule, it's really more of a trend than an actual rule. And there are some elements that actually will do more, many more that will do less than them, specifically our group 1s and our metals in our group 2. So, question. We know that up here, neither Na nor Cl has fulfilled the octet rule. What predictions could we make that would allow us to show that Na is going to donate its electron to Cl, right? There are a couple of different properties that we can talk about. For example, metals. We know they have a low ionization energy and because they have a low ionization energy, much lower than nonmetals, when compared to, and we can compare these to nonmetals. Eh. A much lower ionization energy, which means that it's much easier to remove metals, move an electron from a metal than it is from a nonmetal, specifically in the same period, right? Not only that, we also know that metals tend to have a low electron affinity, which means that they don't tend to attract electrons. But most important of all, I think, is that because of these two, metals always form positive ions. Every single time when a metal atom turns into a metal ion, it's going to be positive. Whereas nonmetals, where they have generally high ionization energy, they have high electron affinity, and they tend to form negative ions. They don't always, but they tend to. And two vocab words we should know. The correct name for positive and negative ions, they have special names, and I forgot if I went over it in class, but a positive ion is called a cation or cation. And I remember that because cations are positive, like a cat paw. Positive. Mew. So a cation is positive, whereas an anion is the name of a negative ion. And I remember that by saying an negative ion. So two little mnemonic devices. So we have a cation, we have an anion. We're able to see that sodium is going to give away its one valence electron to chlorine. So we're going to get something that looks like this. Let's draw them out again. Whew, here we go. Let's see if I can fit it all in one little circle. Whoop. 11 protons, 11 neutrons. And then please note up here, I didn't draw all the electrons. If you really wanted me to draw them in, which I noticed I forgot, there would be 2 electrons here, 8 electrons there, 2 electrons there, 8 electrons there. Okay, so all those of you who think I forgot, sorry. 3, now we're going to have 2 electrons, we're going to have 8 electrons, and overall, this is going to have a positive 1 charge. You don't have to put the 1, you can just put the positive right there. Okay, and let's see if we can do it again. Apparently, I'm making an oval one. 17 protons. Ah. And we are going to have, how many neutrons do we have? 17? Yeah, we did 17. Why not? 17 neutrons. Two, three, two electrons, 8 electrons, 8 electrons, and then this whole thing is going to have a -1 charge. And of course that we see that since these are oppositely charged, we're going to have a nice force of attraction. Isn't that beautiful? Right? It's beautiful. Think about it. Sodium said, hey, chlorine, will you take my 1 valence electron? And chlorine said, yes, yes, sodium. I will take your 1 valence electron. And then they were attracted. Oh, and they form what is called a chemical bond. It's kind of like marriage, only with electrons. This is called a chemical bond. And the direct definition of chemical bond is a strong force of attraction. That's for all chemical bonds, but this is also a very special type of chemical bond. This type of chemical bond is called a ionic bond. An ionic bond is simply a strong force of attraction between oppositely charged ions, right? And the reason we call it an ionic bond is because it has the word ion in it. So when 2 ions are attracted to each other, an ionic bond, okay? Now, let's do another example to show you how an ionic bond can form. Only I want you to notice that the only electrons that are really involved in chemical bonding are valence electrons. So really, it's a pain in the butt to draw this whole thing over and over and over and over and over again, right? You don't want to do it. I honestly don't do it. So we actually have a very special way of showing these different bonding methods, and we call them Lewis dot structures. And a Lewis dot structure would show only the elemental symbol and the valence electrons. Right? And basically the dots are the valence electrons. So we have Na, right? And then we have Mg, which has 2 valence electrons. We're going to draw it like that. Dump, bump. Phosphorus, jumping over to phosphorus. Phosphorus happens to have 5. And there's a very special way to draw phosphorus. 1, 2, 3, 4, 5. And let's do argon just to show you what the full octet would look like. Be 1, 2, 3, 4, 5, 6, 7, 8. Let me write that out for you in case you missed it. 1, 2, 3, 4, 5, 6, 7, 8. So that's how I'm going to draw it, and that's how you should draw it because it shows us a little bit more structure. Now, let's focus back on our friend chlorine. Chlorine has 7 valence electrons. So we'd have Cl, 1, 2, 3, 4, 5, 6, 7. And this is the atom, right? And if I were to draw the chlorine ion, we're going to draw in a special way. 1, 2, 3, 4, 5, 6, 7, 8. We're going to put the brackets around this. And the reason we put brackets is to show who, not how, who, quote unquote, owns the electrons. And of course, this is an ion, but over here for the chlorine atom, it's not just the Lewis dot structure atom, we also call it the parent atom, because it's the parent of this ion, right? This atom turned into that ion. And that's not too significant here, but it is very significant when drawing our cations and their parent atoms. So let's look at Na. Na, so this is the parent atom. And Na plus, we don't have to put the 1, you can. This is going to be the ion. Now I want you to notice how in our Na ion, it currently is drawn with 0 dots. And the reason it is drawn with 0 dots is the Lewis dot structure, not Don, dot structure, is in reference to the parent atom's valence shell. So this is referencing shell number 3. Okay, so what's the power of the Lewis dot structures? Well, the power of Lewis dot structures comes from when we have really anything that we want to figure out the chemical formula. So let's do an Mg and let's do a Cl. 2, 3, 4, 5, 6, 7. Right? And so what could happen here is that Mg could donate its electron to Cl. When Mg donates its electron to Cl, we see that Cl is now fulfilled the octet rule. It has a negative charge. Mg has a positive charge. But Mg is not fulfilled yet. It still has this 1 valence electron that it needs to get rid of to get to the full octet that is below it, right? How does that work? How does that happen? Well, there's not just one Cl in the whole world. Obviously, there's going to be another Cl. So we have another Cl come along, right? 2, 3, 4, 5, 6, 7. This other electron could go to this other Cl. And look at that. Now we have a +2 here. We have a minus. And everyone has fulfilled their octet rule, right? And so this is the Lewis dot structure of MgCl2. There's another way to draw it. We could also draw it like this. Mg plus 2, 2. Notice that's a big number. 2 Cl 1, 2, 3, 4, 5, 6, 7, 8 minus. So these are both perfectly good ways to draw the Lewis dot structure, but the chemical formula would actually be MgCl2. Right? Okay. And that is your introduction to ionic bonding. Thanks so much for watching. I hope everyone has a wonderful day. Bye, everyone.